Oye, Iván, este sábado de conferencia, este sábado, a las 9.
Pues, mañana no, 6. Sí.
Muy buenas noches, bienvenidos entonces a esta nueva sesión semanal del Coloquio de Astronomía, que hoy tendremos un invitado muy especial, ya en breve nos lo estarán presentando. Quiero hacerles una invitación también para el próximo domingo. Vamos a tener aquí en este mismo salón una sesión muy especial, es una sesión de conexión con otros planetarios del mundo, se llama un Domcast. Se trata entonces de visualización científica en vivo. En este caso va a ser directamente controlada, piloteada desde el planetario de Chicago por el doctor Mark Subaro, director de astrovisualización de ese mismo planetario, y vamos a tener entonces la conferencia del profesor Michael Turner, uno de los cosmólogos tal vez más influyentes de nuestro tiempo. Entre otras cosas fue quien acuñó el término energía oscura. Es entonces una oportunidad para discutir, escuchar, preguntar acerca de algunas de las ideas de vanguardia en cosmología. La conferencia se llama Del Big Bang a los multiversos y más allá. Va a tener una duración de 1 hora, es totalmente gratuita, va a ser en este mismo espacio entonces a las 11 de la mañana. Es, como les digo, una conexión en vivo. Vamos a estar en conexión remota con el planetario de Chicago, el planetario Adler, un planetario en Wyoming, el planetario de Denver, el planetario de Colorado, el de Denver, perdón, el de Houston, el planetario nacional de Ghana y un planetario dos planetarios en Noruega. Entonces va a ser una oportunidad de estar compartiendo con gente de todo el mundo una experiencia en tiempo real de visualización del universo, creada por el planetario de Chicago. Están todos entonces invitados para el próximo domingo.
¿Se puede grabar?
Horas. Preguntaba por allá. 11 de la mañana. Domingo 11 de la mañana, en vez de estar en piscina, se vienen para acá.
Carlos,
La ventaja es que salen de ahí,
¿se puede hacer?
y entran al club de curvo y aprender a armar el curvo.
Oiga, pues, no, el programa está completo, pues.
¿se puede hacer live?
No, por módicos 50.000 pesitos, estamos hablando. No, completamente gratis, no se pueden perder esa oportunidad. Bueno, ya pues, Caliche, pues, el director del planetario nos dio, director científico del planetario, ya les dio la bienvenida. Hoy tenemos otra edición especial del Coloquio. Esta es una época de visitantes. Hace 8 días tuvimos aquí a Carmen, disfrutamos pues de una conversación con ella. Y hoy vamos a escuchar a el doctor Alan Hayes, que es vamos a decirle una astrochemist o un astrophysicist. Ok, él le gusta que le digan de las dos maneras. Do you like to be called astrochemist? Is fine, okay. Un astroquímico neozelandés. Que estuvo de visita estas 2 últimas semanas comiendo cosas extrañas, eating strange things, like bandeja paisa, ajiaco, arepa, todos los días huevo, all days you will eating eggs. Okay, y que tuvimos la suerte de, digamos, nos ofrecieron un curso de astroquímica en la universidad. Bueno, la charla que vamos a escuchar, antes de comenzar, before we start, la charla que vamos a escuchar de Alan es una charla, como lo hemos hecho en otras oportunidades aquí en este mismo espacio, en inglés. Nosotros siempre hemos estado, siempre ha habido mucha pregunta de si se puede dictar una charla en inglés completamente en la universidad, en Medellín, sin tener un traductor simultáneo. Ya nosotros siempre nos decían, eso es imposible. Ya llevamos como 5 charlas en inglés dictadas en este mismo espacio del coloquio, y siempre con la misma metodología. Obviamente no se puede entender todo en inglés cuando uno habla español todo el tiempo. Entonces yo voy a estar con Alan. No le voy a estar traduciendo simultáneamente porque aquí el 80% de ustedes entiende perfectamente el inglés neozelandés. Pero yo voy a estar y cada, no sé, 5 slides, cada 3 slides, voy a tratar de hacer un resumen breve en español de lo que él acaba de decir en los últimos 3 slides. Every 3 slides, I will stop you and I will summary, but very shortly, I will summary what you have said, but in Spanish. Okay? So, la idea pues es obviamente que le pongan atención a todo lo que dice Alan en inglés, porque mis resúmenes son muy pobres. Bueno, por el esfuerzo del día de hoy ustedes van a hacerse merecedores a una camiseta, una bonita camiseta, ¿cierto? De la universidad, de la ciudad de Leiden. Estoy viendo si es Science, no dice University. Es de la Facultad de Ciencias de la Universidad de Leiden, en Leiden, Holanda, donde trabajan Carmen y Alan. Esta camiseta es talla M, o sea, talla colombiano. Es la talla de todo lo otro, y si no, se la regala algún amigo. Pero obviamente no tenemos 80 camisetas de esta. We only have one. So, el asunto va a ser al final, vamos a hacer una rifa de esta camiseta con una pregunta sobre la conferencia, sobre la charla. Entonces hay que estar muy atentos. Bueno, advertencia final: Alan habla muy rápido, very fast. Alan speaks very fast. Yo no sé si ustedes han visto El cazador de cocodrilos. ¿Se vieron Cazador de cocodrilos? De Crocodile Hunter. Ok, he is not Australian, él no es australiano, pero el acento es de Nueva Zelanda, que es muy cerca. Entonces el acento es muy duro. O sea, al principio a mí me dio mucho trabajo, pero estoy seguro que con el tiempo van a empezar a entenderle los chistes. Si está todo el tiempo contando chistes, every time you are telling some jokes. So, los chistes no es más difícil de entender, pero bueno, espero realmente que disfruten. El tema es súper apasionante. Si usted se para aquí en Medellín, tiene que recorrer por ahí unos 5.000 kilómetros para encontrar un experto en esto. O sea que ustedes están parados a few meters away from the only expert in astrochemist in a circle of 500 kilometers, 5,000 kilometers. O sea que aprovechémoslo, por favor. Preguntas, cualquier pregunta, English or Spanish, are welcome. Yo las puedo traducir o ustedes las hacen directamente en inglés. So, Alan, we are very happy to have you over here. Please welcome.
Muchas gracias.
Ya aprendió, paisa.
Lo siento, no hablo español. Buenos días, ¿cómo estás? The end. Indeed, I do come from New Zealand originally, via the Netherlands, and I will talk as slowly as I can, which is about as fast as we got up this point in the US. And I'm not the only astrochemist within 500 kilometers, because there's now 13 young Betagenistas, who have started on that path. Don't know if they'll continue. We've had 2 weeks of it from me, and that might be enough for them. Okay, so for this talk, or this discussion, I wanted to talk about stars and planets and things like that, normal astronomical things, but also talk about molecules, which is, that's not an uncommon astronomical thing, but it may be a little bit different to normal. And so this introductory slide with my name and the subject includes stars and planets, and it includes molecules. Because we're not looking just on this left-hand picture, we're looking at stars with a cloud in front of them, a cloud of dust and a cloud of gas, which includes molecules. So that's a picture of all those three things. This picture was made with the Hubble Space Telescope, and that's pictured there, or you could make it maybe with the Very Large Telescope. I always include the Very Large Telescope because it's such a good name for a telescope. I mean, whatever the price for the shirt is, it's not, why is that called a very large telescope? That's clear. That's in Chile, the Hubble Space Station. Hubble Space Telescope is in space. Anyway, so this is a picture of stars with a cloud in front of it. This is another picture of stars with a cloud in front of it, different cloud. Discovered by Barnard in 1968 perhaps. And the thing about this one is the cloud is so thick, it's such a big cloud, you can't even see the stars anymore. It's a black spot. And so that picture on the left, it shows you what you would see if you looked at this with a telescope. In fact, you can look at this with a telescope. You might do it here sometimes, I don't know. Yeah. Actually, it might be in the northern hemisphere, far north hemisphere. So you can look at the same cloud though, not with visible light, but infrared light. That's the right-hand picture. In this case, it's not so black. You can see through it. You can see the stars. They're weakened, but they're there. And so if we're going to study the molecules, we can't see anything on the left. The molecules in this cloud, we have to look at the image on the right. So what that means is that we're going to be using infrared telescopes. So that's not the Very Large Telescope, unfortunately. So that won't be back. So the interesting thing about this picture is that invisible light is black. In infrared light, you can see through it a bit. If you look in the far infrared light, so that's infrared beyond infrared, I'll discuss that maybe a bit later, then it's not just see-throughable, it shines. It's like a very weakly bright object in the sky. You can actually see it like it's lighting up the sky. And that's what this picture is showing. So you might see these white lines, that's the shape of it in the previous picture, and now we see this shining light in the far infrared. And that's coming from dust in the cloud, very cold dust. And we also see that it's not just a uniform blob anymore, it has other things in it as well. So already things are becoming more complicated actually with this picture. So we probably shouldn't continue too far down with this cloud because it's just going to get worse from there. But the interesting thing is that now it's not a black cloud, it's a shining cloud, a beacon in the sky. And that goes for the entire galaxy. I mean, this is a great picture, which I didn't make, NASA made it, but it's fantastic because it shows the galaxy, the entire...
I'm sorry for interrupting.
Time to translate?
It's time, and
please.
There are a couple of people, yes, coming to the auditorium. Bueno, a los que acaban de llegar, estamos con el profesor Alan, con el doctor Alan, que viene de la Universidad Leiden, y la conferencia es en inglés, pero va a estar interrumpiéndolo para comentar un poco lo que está diciendo en español. Pueden preguntar en español en cualquier momento también, porque como lo dijo al principio, esto es como una especie de discusión más que de una charla. Vamos a hablar entonces no de estrellas, sino de las nubes que ustedes vieron al principio, que a veces en el cielo nos tapan las estrellas de fondo, pero cuando las vemos, por ejemplo, vemos en infrarrojo, vemos que son transparentes, ¿cierto? Usted vio la imagen ahorita de una mancha negra en el cielo que había sido observada por Barnard. Thank you very much, ¿cierto? En el visible, incluso al principio se pensaba que ahí no habían estrellas, pero era muy extraño que había ahí un mal olor ahí dentro de esa región, y después cuando se lo observó en infrarrojo se vio que habían estrellas. Pero cuando uno se va a una región del infrarrojo más lejana, no solamente la nube es opaca y se vuelve transparente, sino que empieza a brillar, y lo hace gracias a la luz emitida por moléculas, que es el tema, digamos, de la charla.
Thank you. So this is showing the same idea about the entire galaxy, looking towards the center of the galaxy. The middle of all these pictures is the center of the galaxy, but looking at it with different kinds of light. If we go, actually, the most familiar is the third from the bottom. That's kind of has black clouds, stars, that kind of thing. That's the optical light. That's the normal picture you see with a telescope, with the human eye. If you go down from that, you see light that's X-rays and gamma rays and things like that are generally associated with high energy physics and stuff like that. If you go up on the graph from optical, you see the infrared. And you go beyond that, you see even further in the spectrum from infrared, you start to see millimeter waves, they're called, and radio waves right at the top. And each of these pictures is, you can see it's the galaxy, but they're totally different. Some are black, that visible light, optical light picture, third from the bottom, has lots of black clouds. Some are shining, and some are kind of, even have different shapes than the others. So by studying these things at multi-wavelengths, that is different kinds of light all at the same time, we can study different things. And since I'm talking about molecules, we're talking about everything that's upwards from optical, the infrared and radio waves. That's a great picture. I really like that one. And so this is the physics picture of what we just saw. So we know that we can see only a small amount of the light that exists in the universe. The visible light, you can see some there with all the colors. And we're talking about radio waves, microwaves, infrared light. That's going up from that. That means the light has a longer wavelength. The X-rays and the gamma rays from particle physics and things like that are all the shorter wavelengths, very small waves. So this is really the idea that we're only really capable of seeing a small part of the universe, but with telescopes and detectors and technology we can see more. But there's a problem. There's always a problem. In this case, the problem is the atmosphere. The reason, actually, that we can see visible light with our eyes is because, for one thing, the sun produces visible light. So if we see things during the day, it's because our eyes are tuned to that. But also it's because the atmosphere is transparent. You can see through the atmosphere, unless it's a lot of cars that day and perhaps the clouds are a bit low or something, or it's nighttime. But this is the problem. This shows a picture of all those wavelengths, and it shows a picture of how they're affected by the atmosphere. All the blue wavelengths don't make it through the atmosphere. That includes, in this case, the microwave, and, oh, that's the wrong way around. All the white wavelengths don't make it through the atmosphere. Sorry, I take that back. So that includes the visible part, DIS, that's the part we can see, the universe's atmosphere is transparent, the microwaves, and all these infrared parts. This is the part I said was good for seeing molecules in that interstellar cloud is completely absorbed by the atmosphere. And what that means...
Yes. Esta imagen es muy importante, me imagino que todos la entendieron, y si no vamos a volver a explicarla, aunque ahí están explicadas algunas cosas. Entonces, lo que aparece en azul es la parte del espectro electromagnético, o sea, las formas de luz que pueden pasar y verse desde la superficie de la Tierra, ¿cierto? Y eso incluye el visible que aparece ahí como bis. Lo que aparece en blanco es lo que no logramos ver. Aquí abajo aparece la longitud de onda y el nombre de cada frecuencia. So, thus the images we saw before of the Milky Way, ¿cierto? Las imágenes que vimos antes de la Vía Láctea, not everyone was taken from the surface of the Earth. No fueron todas tomadas desde la superficie de la Tierra. Which ones were taken from the surface and which ones?
Let me answer that in pictures.
Okay. Great.
I lied. The Very Large Telescope has returned. And it's much bigger than it looks in that picture, actually. It's very large. So that's for looking at visible light, which we can see through the atmosphere. There's an aeroplane next to it. That's because if you go to the infrared, you can kind of see it if you go in an aeroplane. You're above most of the atmosphere. If you go further in the infrared, you need a spacecraft. In this case, there's the Herschel Space Telescope orbiting the Earth, or was orbiting the Earth. Fortunately, if you go to even longer wavelengths, and if you're here last week, you heard all about this, you can go back on the ground. In fact, that's not really back on the ground, it's on the top of the Atacama Desert Plateau, 5,000 meters high, so still above lots of the atmosphere, but on the ground. That's the ALMA telescope, which is a modern marvel of astronomical engineering. So really everything we're doing requires lots of different technologies and things like that. So this multi-wavelength kind of way of looking at the universe means you have to have lots of cooperation between people working on different kinds of telescopes and so forth. It's a group effort. Okay, and this is going back a little bit, this one, 17th century, to the Netherlands, I believe, Christian Huygens. He observed a dark cloud, and he drew it by hand. In this case, he couldn't photograph things in those days, and he observed the Orion Nebula. And what he's drawn here, he's drawn all the stars in Orion as stars, and he's drawn a white patch, which is actually the part that's actually somewhat illuminated in the nebula, and a dark patch around it where the nebula is darker. And so this is some time ago, And it's already an interesting graph. I'm sure this really made the news in 1694 around the European science circles. But if we look at it now, and we're using not just visible light, we're also adding a little bit of infrared just to spice it up and making that appear in this one photograph. The Orion Nebula is even more amazing than Christian Huygens could have imagined. Just to give you some bearings there, he drew 3 stars on an angle kind of just outside the white patch, and then there's 4 stars inside the white patch. Keep your eyes on those 3 stars in a row, and those are the 3 stars just below the center in this photograph. So, I mean, you can photograph this with a regular telescope and a regular camera, and it comes out pretty well, actually. But he was drawing the center of this picture by hand. Now we can photograph this with visible and infrared light together. And you might argue this is a beautiful image. I don't disagree. Like, it's one of those classic astronomy images that appears everywhere. But myself, I began my studies as a spectroscopist and a chemical physicist. So, we have a more closed-minded view of beauty, actually. So this was nice, I didn't mind it, but then we got deeper into the data, and oh my god, that's amazing. This is the Orion Nebula as it should be seen.
Solo para ponerlo en contexto, entonces, atención, primero la imagen que viene a continuación, que es la de todos los libros, está un poco, digamos, endulzada con infrarrojo. O sea, tiene algo de infrarrojo, por eso es tan bonita, no se va a ver nunca así. Y bueno, al final me parece muy importante señalar lo que acaba de decir Alan, lo que a todos nos parece bonito, que es la nebulosa de Orión, así en esa imagen tipo del centro de los libros, a alguien que fue formado como un físico molecular, un químico molecular, pues no le parece realmente tan espectacular. Esto es lo espectacular.
It is spectacular. No, but the question is, what is it? That's a good question, actually. What this is looking in the far infrared, so invisible to our eyes, and it's not creating a map of Orion, a photograph. Instead, it's looking at individual wavelengths of the infrared. So this is a spectrum. It's looking at fine spacing between wavelengths. Like if you took the difference between red and green, for example, your eye can tell the difference between those 2 colors. This would be red and very slightly less red would be this kind of scale. It's very sensitive to small changes in infrared color, the spectrum. And where are these lines coming from? They're coming from the molecules. This is the signature of there being molecules in space, this kind of thing. That's why I liked it, actually. And you think, okay, it's a lot of information in this graph, a lot of different molecules. In fact, it just looks like kind of a noisy line, actually. And it's not even the beginning, because if we look at this graph, and that's in the top right-hand corner is that same picture. We zoom in on a little piece of that, it's the light blue area. We zoom in on that little piece, we still have lines. I mean, this is like a field of grass, where every piece of grass is something interesting for a spectroscopist. In this case, we're looking at one molecule, is labeled some of those lines, that's methanol.
Yes. Entonces, muy importante, esto que estamos viendo aquí es un espectro que es la descomposición de la luz que emite la nebulosa. En este caso, en una región, digamos, lejana del, digamos, el rojo, muy rojo. Esto es muy rojo. Pero lo más importante ahí es que estamos viendo un pedacito muy chiquitico del, digamos, de ese rojo. Y lo que están viendo ahí ustedes es la emisión de la luz por las moléculas. Entonces hace una analogía muy interesante, y es que esto que estamos viendo aquí, así, haciendo un zoom in en la imagen, es como buscar los detalles en la hierba, ¿cierto? Donde descubrimos finalmente los detalles del metanol. Metanol is poisonous, right?
You shouldn't drink it.
You shouldn't drink it. Yeah. A lot of people that drink, especially during durante la Feria de las Flores, here in the
flower festival.
Yes, we drink a lot of methanol.
Well,
no, I mean a lot of methanol because we drink a lot of bad liquor. Well, el alcohol falso le echan una mezcla de etanol y metanol. I'm sorry, a chemist. Well, no, correcto. Por ejemplo, entonces le echan. Por eso es que el alcohol adulterado le echan metanol. Para más barato, ¿cierto? It's far more cheap, right? It's because it's very expensive. It's expensive. Methanol is more expensive than ethanol, or not?
Una botella de metano cuesta 5 litros, vale 150.
5 liters, $30.
I think both methanol and ethanol are both quite cheap in principle. I mean, yeah.
And it's produced in the nebulas. The nebula.
This would be an expensive way to get methanol, yeah. But I was worried when I put this graph up, actually, and your description helped, that I worry people might think, I vaguely remember this from high school and it sucked then. I don't know if I want to look at this now, but think about this for a moment, is that you have the Orion Nebula. I showed a photograph of it. It's 1,000 light years away, and we know what's in it. You can actually measure what's in the Orion Nebula. We're not really sure what's in the next room right now. Probably some methanol by the sounds of it in the street, but I mean, that's really kind of an amazing thing, I think, to be able to tell that. And this is only one of the molecules. Look at all the lines. There's a lot of other things we know about this.
There's a question right here. Do you want to make it in English, or do you want? Why there is some gaps between the lines?
Yes, because the telescope had more than one. Well, the spacecraft had more than one telescope detector on board, and it's quite difficult to measure spectra in the spectral range on a spacecraft. So they had to have several different detectors for different ranges of wavelength, and some ranges there's just no technological means to make a convenient measurement. So it's because there's more than one telescope photo camera on this, and they don't overlap.
I have another question. This kind of spectra is the same kind of spectra that you get when you have an alcohol test in your blood. ¿Cierto? Cuando le hacen un examen de sangre si tiene alcohol, estos son los mismos tipos de espectros que ven ahí para ver si uno está alcoholizado. ¿Cierto?
No.
Okay, very short answer.
I'm pretty sure no. I mean, you could get the Herschel telescope, point it back to the ground,
and see where is the people in the Festival of Flowers.
Yeah. And like I said, there's other molecules in there as well. I'll start at the top and I'll go through them one by one, okay? We'll discuss them.
We have until 11.
Yeah. So there's a lot of them. In fact, there's more than 200 have been seen in space, 200 kinds of different molecules. H2, I'll just discuss one. H2, that's the big one, because most of the universe is, well, most of the baryonic matter, the matter we understand of the universe, is hydrogen, so that's an important molecule. But I won't go through them one by one. But I'll show you the rest of the list as well, just to make it clear that it's a long list, including some weird things like this football-shaped molecule at the end. So that occupies a lot of people's time, actually, this kind of stuff. Okay, so that's interstellar cloud, just a black spot in the sky. Orion, this is that interstellar cloud again. And this time we're looking at it with another photograph, this time deep in the infrared. So that's on the left, visible light, basically. On the right, infrared. And now we're seeing not just a cloud that we can't see through, the cloud is shining again. It's shining in spots, in points. And that's the evidence that there's stars inside the cloud. In fact, there's new forming stars, and stars that formed recently, and stars that will form soon. There's a whole generations of stars forming inside this cloud. This kind of interstellar cloud of gas and dust is where stars form. This is the stellar beginning, the stellar nursery, exactly. And just to give you a quick astrophysics discussion, and because I'm an astrochemist, not an astrophysicist, I'm always a bit careful about this, so I don't want to go into too many details. On the left is part of the Orion Nebula. It's just dust and gas, but it has its own gravity. I mean, it's really low density. It's much, not like being in this room with this level of gas. It's much less gas anywhere, but it's big, so it has a lot of gravity, and it collapses under its own gravity. It just collapses to a point in the middle. And that middle gets denser and denser and denser, until eventually it becomes the beginning of a new star. And that's the second step on this three-step graph. There's a beginning of the star right in the middle. It's all collapsing to form that. And the star forms not just as a single point, it forms as a point or so forth, but a much bigger disk. In fact, there's an artistic impression of what one of these disks must look like shown there. So that's the astrophysics done. We can go back to the molecules, great. So this disk though, that's a pretty good artistic impression, and it doesn't really look like that. That's also important. And it turns out they do. This is photographs of some of these disks inside the Orion Nebula, taken with the Hubble telescope. So we're seeing, I mean, it's a bit blurry because it's very far away, not that easy to photograph, but we're seeing these disks around these stars. And on the bottom left-hand one, you can see the size of the solar system. So they're about as big as the solar system.
Ok, como vieron todos, yo creo que todo está muy autoexplicado. Yo solamente resaltaría el hecho de que es impresionante ver la nebulosa de Orión, él lo resaltaba, y ver estos puntos en el infrarrojo lejano, la imagen que nos mostraba. Can you show us the image? We want to see it. I want to see it again, the image on. Yes. Es muy interesante ver en el infrarrojo lejano, cada uno de esos puntos es una estrella que está naciendo en este momento. O sea, es una cosa, pues es impactante. Y el otro detalle importante para recordar es que al nacer las estrellas siempre están rodeadas como de un disco. De poner la analogía como si fueran los anillos de Saturno alrededor de la estrella. Y esta es la imagen de ese disco. Great.
Yeah, this really blew my mind the first time I saw this a few years ago. But this is old technology. This is what protoplanetary just looked like in 2011, you know, in 2012. People were impressed back then. But then they built the ALMA telescope. And this was, it was built for many reasons, but partly it was built to look at these things, stars forming. So let's look at a picture with the ALMA telescope. So now, that's a picture of ALMA on the bottom right-hand side in the mountains. And that's a picture of a protoplanetary disk around a new star taken at ridiculously high resolution. It's like having a zoom lens turned to 1,000,000, or more than 1,000,000, I guess. And shown there is another orbit, this time of Neptune, showing this is a bit bigger than our solar system, but not that much bigger. Okay, and so what are we looking at? We're looking at a star in the middle, the dust around it, and it has, this is what made the news with this picture, it has these rings in it, exactly like the rings of Saturn. This had never been seen before. There were theories, there were people saying the theories were wrong. Now we know the theories were right. There are rings around some of these things. And we know more than that now as well with ALMA. And now we're getting back to molecules, that's my subject. Because this is a picture by an artist, a nice one, of a protoplanetary disk around a new star. And there's a star in the middle which is shining, so it's producing a lot of light and heat. And so if you get further and further away from the star, it gets colder and colder. The same in the solar system. I mean, Pluto is just a ball of frozen nitrogen, we now know, ice. And so that's shown in that picture, that the further you get from the star, the more ice you have. And this was another theory and a nice painting, but also this was tested by ALMA. ALMA could look at this disk. This is a disk, a different one, but similar. Looking down upon it, you see it has the same kind of shape, about somewhat bigger than the solar system. And they've looked at dust, that's the left one, that's interesting, but they've looked at carbon monoxide, which is a molecule, and it's a molecule that can freeze, it can turn into ice like that. And so it has a lot of blue in the middle. That means there's a lot of carbon monoxide in the middle, but not much on the edges, and that's because it's turned to ice, which is interesting. But I think the one on the right-hand side, this is another molecule, N2H+. Let's just call it another molecule. This time it has a lot of blue in a ring and nothing in the middle. There's no N2H+ in the middle. There's a ring, and then it kind of disappears again. And now we're really doing astrochemistry, because what happens is N2H+ is eaten up by carbon monoxide. If you have carbon monoxide, you don't have N2H+. That's just some chemistry which I'll spare you the details of. So what it means is that in the middle there's carbon monoxide eating up the N2H+, and then it's gone. So the N2H+ becomes a ring. And that tells us that definitely the carbon monoxide is only in the middle. It's frozen outside that point.
Yes. Esto es importante porque esta es la diferencia entre astroquímica y astrofísica, ¿cierto? Lo que esta imagen que aquí es muy diciente. Entonces ustedes ven ahí las moléculas que se ven a distintas distancias. ¿Qué pasa? Entre más lejos estás de la estrella, más frío hace, se congelan las moléculas. Pero entonces, lo más importante es ver la última imagen donde hay un agujerito en la mitad, y ese agujero en la mitad indica que no hay de esa molécula que la vamos a llamar a partir de ahora una molécula más, N2H. Y la idea de que no haya N2H en el centro se debe a que hay una reacción química con el CO, con el monóxido de carbono, que la destruye, ¿cierto? Más allá de esa distancia donde está ese huequito, el CO, el monóxido de carbono, está congelado y no puede destruir el N2H, ¿cierto? Entonces, ahí lo que hay es la evidencia de reacciones químicas. Esa es astroquímica. Okay.
Okay, I think I put the word planets in the beginning, so I should talk about that. So there's a picture of that same Alma photograph again. The disk has a name, it's called H-Al Tau, in case you read about it later, you'll know you've seen it. And it has these rings, which I said was the interesting part when it was discovered. And there's a theory about that. Where do these rings come from? And it comes down to the story of planets. So there's a somewhat technical picture on the left showing a star, and it's like a cut through the disk around it. It's like showing the material that's appearing in the Alma photograph. And it includes the grey material, the grey coloured in bit, that's gas. And it includes bits of dust, that's the black spots. And that's what this disk is made of in the beginning. But those black spots, the dust, they begin to stick together, forming larger pieces of dust. And the large pieces of dust stick together, forming small rocks. And they stick together, forming large rocks. And this is where people get a bit uncertain, but at some point they stick together, forming small planets, or small moons, and they stick together, forming bigger and bigger, until eventually you get planets forming out of that dust. This is cutting edge stuff. I mean, people are not sure about the details, but this is what we're discussing now. And part of that thing is those planets, they have a habit of eating up all the gas and dust in the disk and making a ring, or possibly a hole in the middle, but possibly a ring. So these rings we're looking at, we can't see any planets there, but we could be looking at the gap made by a planet, the effect of a planet on the disk. That's what's really interesting about it. And these planets are not like the Earth, 7 billion years old or so, 12 billion. Not my field. But these planets will be less than 10 million years old, possibly less than 1 million years old. So this is planets forming. This is the next generation. Eventually, this disk is gone and gets eaten up, and you end up with planets at the bottom, like we have in the solar system.
Creo que lo más importante para resaltar es entonces que ese espacio ahí donde no hay luz en el disco es debido a la presencia de un planeta que no podemos ver. Lo impresionante también, ya es lo que decía al final, es que este objeto tiene 10 million years. The age of this object?
Up to 10.
10. Tiene 10 millones de años. O sea, mientras que el sistema solar tiene 4.560 millones de años. Estamos hablando de una cosa que está recién nacida. Ahí hay un planeta en formación.
Yeah, so I should point out that this is not all telescopes. Oh, actually, I wanted to make one more point. Actually, I don't have a slide, I'm sorry, but you've probably discussed the gravitational wave detector measurements from earlier in the year. So all those Milky Way pictures I showed right at the beginning were infrared and visible light and X-rays, things like that. And so we thought this is how we see the universe. We use light. But now we have a new way to see the universe. I mean, that really is revolutionary, that we can one day, not yet, but one day perhaps they'll be able to make a picture, not of the Milky Way perhaps, but of the universe or the local universe in gravity waves, in terms of large black holes and things. Take a while, but that's going to be interesting.
Alan está diciéndonos que un día vamos a ver una imagen del universo, no en imagen en infrarrojo, en radio, sino en ondas gravitacionales. We are expecting for that day.
But this slide is not about that. This is about our solar system, because it's the one solar system, the one set of planets and the one star we can kind of touch. I mean, most of what we assume about other stars and about other forming solar systems is kind of based on what we can see in our local back garden of what our solar system is like. So this was another revolutionary step in the last year and a half, was the Rosetta spacecraft. You would have discussed that, I guess, as well at some point.
Of course.
And so it visited this comet. Let's call it 67P and leave it at that. and
Churi. We call it Churi.
And it didn't just look at it with in terms of radiation, it just detected the bits of dust and material that the comet was ejecting, and it made a spectrum, which is a different kind of spectrum before, but similar. And because it's touching it, it can detect it to a much higher degree of precision than looking at something far away. And the thing about comets is comets are thought to be the earliest part of the solar system. So when this is forming, the big black spots are forming out of the dust. Comets are forming then as well, but are forming so far from the star that they don't get included in the planets. That's why there's comets which are not included in the planets. Eventually, they come back to the star. They come back to the center of the solar system, and we can visit them with a spacecraft. But that takes billions of years. So this comet is kind of like a piece of the original solar system before the planets formed. So we're kind of studying not just the comet itself, but we're studying what the solar system was like before the planets formed. And they discovered some things. Oxygen, it's an important molecule. Probably know that one. There's methanol in that picture, by the way. Looks like there's about 1.5 times more oxygen to methanol, which seems like a very dangerous high ratio of methanol, actually. So this is the same idea of looking at these molecules, and it's not all good news. I mean, people come up and give these talks, and they probably sound pretty confident, like, I know it all. I looked it up on Wikipedia before I stood up here to make sure I really knew it. Don't look on Wikipedia to see any of these pictures, you won't find any of them. But this was the first time a molecule was detected in space, 1922. That's not the original picture of it, but it's a new version of it. And so the first molecules that were ever seen in space, don't know, unknown. This is the dirty secret of astrochemistry, is that no one figured out the first molecules that were seen in space. They look like that, kind of a little dip with three extra little dips on it. But a real mystery, actually.
Incredible. Still.
I went to a conference about this 2 years ago, and it was the conference 10 years later than the previous conference on the subject, and they didn't really have much to say. Not much progress. That's not true.
1922, la primera molécula descubierta en el espacio, en el medio interestelar, y todavía no tienen ni idea, ni los más avanzados astroquímicos. Nos contaba que estuvo en una conferencia de expertos, y en 10 años no han progresado, no han podido identificar. Why is that? ¿Por qué no han podido identificar?
It's because they're probably a kind of molecule that's very large, like many atoms. And the thing is, when you have many atoms, you have a lot of possibilities how to arrange them, how many atoms to include, that kind of thing. So it's actually probably not just one molecule, but a big class, like a category of molecule.
Oh my goodness.
Yeah, so
es una molécula muy grande.
Yeah. Sorry, that's what I should have said.
Fast translation.
It's a big molecule.
Now you explain the rest. In very good English, very well understood.
Yeah, I'm doing well.
You're doing well, very well. We have people seeing.
Why couldn't it be a mistake in the measurement?
Good point. Well, so this is one measurement, but there's many others of similar things, and I mean, it's been observed for almost 100 years now, and so I think all that kind of thing's understood. And part of the thing that's interesting about these is you see them by looking just out to space, and wherever you look, you see them, but they change a little bit. So there's, for example, if you look towards a bright star, some of these peaks change how deep they are. So there's other details that do show there's something physical going on, but the exact cause is still unknown. Yeah.
Entonces, no es un error. Preguntaba que si era un error, y no es un error porque se ve en todas direcciones del cielo. Entonces.
And this is kind of the future, actually, or it's happening, but it's really just getting started. Now we're looking at planets, but exoplanets, so around other stars. But we're not just looking at the planet, we're looking at the atmosphere of the planet. So if this is a planet, the atmosphere is just a tiny layer on the surface. These planets actually have a bigger atmosphere than we have, I should say that. It's not as bad as the Earth, but it's still just a little layer. In this case, the way you do it is you have a star, that's some other star. The planet's between us and the star, so the light is shining past the planet, and some of the light is shining through the planet's atmosphere. That gives us a kind of spectrum like that. This is a model spectrum, and tells us what molecules are in the planet's atmosphere. And this is beginning to work. No one's seen methanol yet, which I guess is a shame. Carbon monoxide, another poison. Titanium oxide, I don't know if that's poisonous, and
This is good for a bicycle.
and some H2O, some water, which is good, I guess. So this is a new place in the universe where we're just seeing molecules for the first time.
Es interesante lo que dice de que es, pues obviamente esto es el espectro de la luz pasando a través de la atmósfera de un exoplaneta y ya están empezando a detectar moléculas. Es un logro muy grande, pero no han detectado todavía metanol, monóxido de carbono. Yes. Only, yes, some water.
Some water.
Yeah.
Water. Okay, I think I've only one more slide.
Okay.
Which is the future of the subject, and with astronomy, without a telescope, it's quite tough. I mean, Christian Huygens did a good job drawing the Orion Nebula, but that was a previous generation of technology, Christian Huygens' pencil. And so this is the future, and this one's great. This is the extremely large telescope. So which is bigger? What are they going to do next?
The overwhelming large telescope.
ludicrously large telescope.
Yes.
So that's very impressive. That won't be built for some time, another almost 10 years. On the other hand, there's a new space telescope, the James Webb. You've probably heard of that as well. That's the successor kind of to the Hubble telescope. So this is the next generation of Hubble. Hubble's probably the most successful telescope of all time in many ways. And so this will be starting to give us new information probably 2019, maybe late 2018. So this is, when they saw the rings in the protoplanetary disk of HL Tau, that was just confirming theories, breaking other theories. It was a whole new world just beginning to open. We don't know what James Webb Space Telescope and eventually the ELT will tell us, but it's going to be methanol. And that's all I was going to inflict upon you today, unless you have some questions.
Thank you very much, Alan. Okay. Ok, al final estamos hablando del futuro, obviamente, y lo más interesante ahí es decir que todos estamos muy expectantes de si lo que nos ha mostrado Alma ya nos impresiona, imaginen lo que va a pasar el día que empiecen a salir datos del James Webb Space Telescope. If it's success, it opens. El telescopio se abre como una sombrilla en el espacio, pero es una operación bastante peligrosa.
You know that an X-ray telescope failed earlier in the year. Right? There's a Japanese telescope.
Oh, okay, this year.
Yeah, and it unfortunately it lost control and whatever, and so it can happen.
Claro, hubo un telescopio de rayos X japonés que falló, no hubo manera de recuperar. Okay, Anne, while you are thinking on a question, a very difficult question because this chart worth it. Les pregunto, ¿alguna pregunta? Repito, hay que aprovechar, estamos con un astroquímico, el único en 5.000 kilómetros a la redonda. Entonces, preguntas para Alan. Alan.
Hi Al. Can you go back? I don't know how many to the spectrum that we don't know what it is. That one, no, back.
You think you recognize it? That would be great.
No. I could try. My question is, in the image under, it says, I don't know what letter that it was, but it is in Ophiuchus, right? That is a star in Ophiuchus. The spectrum is specifically of that star, or
So the top spectra was kind of a promotional poster showing all the lines observed anywhere.
Yeah.
Basically, the bottom graph, you're right. So this is showing is the light from the star, actually. And the star kind of produces light continuously. And the name of the star is Zeta Ophiuchus. And in front of the star is a cloud of dust and gas. In fact, the picture I showed on the first slide is that cloud. So there's kind of a connection there. And so the cloud is absorbing some of the light because of the molecules, but only in that particular range of wavelength.
So the material, the molecule, is in the cloud, not in the star.
Well, either in the cloud or somewhere in space between us and the star, but probably in the cloud, I guess.
Bueno, está preguntando por este objeto Zeta Ophiuchus, que era la línea, si la línea estaba en la estrella o en el medio, entonces está, o está en la nube que está entre la estrella y nosotros o en el medio interestelar. More question. I have a question. How much time should a molecule wait to find another molecule in the interstellar medium? ¿Cuánto tiempo se demora una molécula antes de encontrarse otra molécula en el medio interestelar?
That's an excellent question.
I deserve the chair? No.
I didn't ask it, you asked it. So that does vary a little bit. If you go somewhere really in the middle of nowhere, like between stars, not even in this molecular cloud in front of Zeta Ophiuchus, there's probably one molecule per cubic centimeter box, roughly. So if you had a cubic centimeter, it'll have one tiny atom in it. I mean, in the air, there's 10 to the power of 19 atoms per cubic centimeter, so 0, 0, 0, 0. So in that case, you have a collision only once about every month to a year. So there's a hydrogen, probably a hydrogen atom, I'll tell you that, flying through space. And it's flying through space at about 400 meters per second, so quite fast actually. And finding nothing. There's really, takes it a year of flying through space at 400 meters per second before it finds another hydrogen molecule. And then they just bounce off, nothing happens.
So, un mes. Ok, let's continue. No, la idea es, en un centímetro cúbico del medio interestelar donde no hay nebulosa, hay una sola molécula, o un solo átomo, ¿cierto? En el aire hay 10 a la 19 átomos. Entonces, claro, como hay tan poquitas, ya vuelan sin encontrar ninguna por entre un mes, meses o año, o un año. ¿Te imaginas? Una molécula, un año sin encontrarse absolutamente nada. Andrew. Ah.
I was perfectly listened to you.
Ah, okay.
When you're looking for life in exoplanets, is there a specific kind of molecules you are searching for, besides water, of course?
Yes. Water is really common in the universe. So you probably need water for life, but finding water doesn't tell us there's life, unfortunately, because there's probably water lots of places. But there is one, O2. I mean, this is not the final word on this, but we know O2 only appeared in the Earth atmosphere when life first started producing it. And we know that you can have more details. You can compare the O2 in the atmosphere to the CO2 in the atmosphere. And that ratio can tell you that there must be life producing it, because life is not like other things. It's I don't know the word. It's an unstable chemical reaction. It fights entropy or whatever, so unusual things happen. And so this was kind of the interesting thing about the Rosetta Comet mission, because they found O2, and there's probably not life in that comet. So that's put a bit of a damper on that theory, but those are the key things, yes, to try and measure those molecules, O2, CO2, and perhaps they've thought of some others.
La pregunta es ¿qué se busca cuando se busca vida, ¿cierto? A través de la química? Entonces, ahora nos responde que, por ejemplo, buscan la molécula de oxígeno. Although I have read, because this is my area of expertise,
that, sit down.
Yeah, that if you have a planet full of CO2, which is a very common molecule in planets, exposed to the ultraviolet and X-ray radiation from an active young star, you will have a lot of O2, a lot, because CO2 gets destroyed, photolyzed, and then you will have a lot of O2 telling the astronomers, okay, we have photosynthesis, but no. Yes, so you need to detect O2 in combination with something that can exist simultaneously in equilibrium. For example, methane or something else.
That sounds pretty right to me, yeah.
Right. El oxígeno también puede aparecer si un planeta es iluminado por una estrella con luz ultravioleta y rayos X. Y uno dice, eso está lleno de oxígeno, allá deben haber plantas, y no. Posiblemente eso os engañaría. Hay que buscar oxígeno y, por ejemplo, metano. En Mars, hay metano en presencia de CO2 y la gente están sorprendidos porque el metano no dura mucho en la atmósfera y esa es realmente una molécula mucho más importante. Metano es probably most important. Una pregunta, sí.
Hi, doctor. The molecular astronomy is possible applying to black hole research for the spectrum or no?
Interesting.
Astronomía de agujeros negros.
I don't know of any specific science of molecules in black holes. I think the main reason would be that black holes, if they're accreting material, are quite energetic objects. They emit a lot of X-rays and UV radiation, which is death to molecules. But saying that, it's certainly possible that some of the simpler molecules, perhaps the H2 molecule itself, is an interesting way of looking at black holes. You can learn something about that accretion by studying the molecules that can survive there, but I'm not sure any details about that one. So.
Ok, no hay muchas moléculas porque hay muchos rayos X que destruyen las moléculas, obviamente, pero tal vez sería interesante buscar moléculas como H2. I have another question, a continuation from the previous one. If one molecule or one atom hits another one in 1 month, how can be a chemical reaction? You need a lot of hits to get methanol from CH and O.
Oh, you have more than a month.
Obviamente, si hay la pregunta mía era si hay un choque cada mes, ¿cómo puede haber una reacción química? Entonces la respuesta es, pues, en estas nubes ocurre, pues pasa muchísimo tiempo.
I mean, perhaps another important point is that when you start to have not just the middle of nowhere space, but the interstellar clouds, so that's where it's a bit denser or maybe a lot denser than elsewhere. Eventually it forms a star, and stars are very dense, so eventually it gets dense. And so things speed up when you get into that situation as well.
Okay.
We're still talking days.
Ok, existen lugares más densos donde ocurren estas cosas un poco más rápidas, no solamente los lugares pues, completamente vacíos. ¿Más preguntas?
If all nebula are produced in supernovas, which they have the tendency to expel the clouds away, what is the force that starts this encounter between molecules that are supposed to be drifting away from each other?
Yes, you've gone to the next step of stellar evolution, and you're right, is that once these clouds form, and stars form inside them, some of those stars are massive enough they become supernova, and that just blows the cloud apart, exactly, you're right. And that blown apart cloud drifts through the interstellar medium and eventually becomes part of a new cloud somewhere else. It's kind of a cycle of things becoming a cloud, exploding and becoming just diffuse again, and then recondensing. And the important condensing part, that's your question I guess, was mostly self-gravity eventually. But in the beginning, the universe looks like it's a quiet, still, motionless place. But actually it's full of gas at low density, which is swirling around like a hydrodynamic fluid. And in some places, it just comes together. It forms a turbulent eddy or a collision between different parts of the universe gas. And there it becomes denser. And when it becomes dense enough, gravity becomes important and it starts to condense further. And that's when you have the next generation of interstellar molecular clouds and stars.
Thanks.
pregunta era que las supernovas tendían a dispersar los gases y cómo era posible entonces que pudieran, si te interpreto bien, digamos, existir estas nebulosas. Entonces Alan me explicaba que hay mucho en el medio interestelar, hay mucho gas por ahí y la dinámica vuelve y junta el gas. My last question, it's not your last question, it's my last question. Okay. The question is, do we have here some water? I want that you tell us the brief story, the brief biography of one of these molecules here. Okay, very shortly. Where this molecule comes from the beginning, starting from the beginning.
So they were down by the river of the valley of this valley. They had the bottle.
Down to the Big Bang. Quiero que me cuente la historia.
Hang on. Okay, well,
No.
Correct me if I'm wrong about some of this stuff, but there was hydrogen. Eventually it formed a star. In that star, when it exploded, it formed oxygen in small quantities. This happened multiple times until there was a reasonable amount of oxygen. Eventually that oxygen was floating around in an interstellar cloud, like the ones we saw, the dark clouds. And at that point, there's some other details, but at that point, a lot of the oxygen froze out onto the surface of actually the dust grain. So it becomes like a dust grain with ice around it. Hydrogen landed on the dust grain, bonded with the oxygen, making water, H2O, one oxygen, two hydrogens. Then it waited, and it drifted around inside the cloud for another few million years. Then eventually a star formed somewhere, and that star formed a planetary disk around it. Planets formed inside that disk, and some of that water from back in the early days of the dense cloud, before the stars were even there, drifted onto the planets. Maybe it came later in the form of comets, like the Earth probably did. Maybe it came when the planet itself formed, like the planets in the outer solar system. And it's been there ever since. And you drink it and you think, that water's ruined now, but it's just going to come back around again.
Ok, thank you very much. Entonces, muy interesante porque entonces el agua que nos estamos tomando se formó en un grano de polvo interestelar. Cuando el oxígeno que habían producido las estrellas previas se congela en la superficie del grano y sobre el oxígeno aterriza hidrógeno y ahí se forma la molécula de agua que después queda flotando por ahí en la formación del sistema solar y eventualmente llegó a la Tierra tal vez en la forma de cometas. So this drop of water tastes as interstellar grain, something like that. You are drinking some byproduct of an interstellar grain. Esto sabe a grano interestelar. Para que lo tomen con cuidado y con veneración.
And if you want to investigate that water further, you're going to have to find the guy who operated the computer at the beginning. I think he's carrying it around, I don't know.
Okay. ¿Quién será Carlos? Sí, el relato. Okie dokie. Okay, more questions? Or we need to invert the direction of the questions. And now we need one question from you. But slowly, because people start to answer like crazy.
I do have a question. I don't know. You have to moderate the question, I think.
So you have the question.
Yeah.
Please hear it. Okay. Let me think. Sin traducción. Let's do it without
without calculators. You don't need a calculator for this question.
No. I'm thinking about to translate the question. Okay. Primero vamos a ver sin traducción, a ver si alguien se atreve. And very slowly. Okay, first question. Let's rehearse using one pen. Okay? El primer concurso es un lapicero de la Universidad de Leiden, directamente de Holanda, la tierra de Huygens. Okay. So, simple question for a simple pen.
Okay. I showed a long list of molecules earlier, all the molecules that have been seen in space. What was the first one?
¿Cuál fue la primera molécula que se descubrió en el espacio? I saw this hand over there. Your hand. ¿Quién la levantó tú primero? Okay. Hidrógeno. Hydrogen.
Sí.
Okay. Muy bien. It worked. Okay. Let's see. Another simple question. Okay.
if you looked at the Barnard 68 interstellar cloud, I showed it before, and if you looked at it in the infrared and the visible, which one might show you some molecules?
¿En qué longitud de onda se ven moléculas en el Barnard? ¿En el infrarrojo o en el visible? A ver, Jonathan. Infrared.
Sí.
Yes. Great. Aplausos para Jonathan. Y a propósito, si alguien se encontró dos láseres, la conferencia anterior, están embolatados, que los prestó Jonathan. Muy bien. Third question.
Third question.
This is the important one, or
No, there's
we have
one more pen.
One more pen. Very important pen. These pens have been built by Dutch people.
It should still be harder though, right?
This
That's a quality pen.
Yeah. Okay. Pero vamos a empezar con otra, una más durita, pero listo.
Okay, so I showed a graph showing the parts of the atmosphere you could and couldn't see through. You could see through the visible atmosphere. You could see through some of the infrared atmosphere. What other wavelength can you see through the atmosphere?
¿Qué otra longitud de onda se pueden ver a través de la atmósfera, distinta del visible? This guy understand the question in English. Radio.
She was here last week, wasn't she?
Okay, great. Aplausos. Muy bien. Oh my goodness. So, this serves special rules. Okay? Solo se puede levantar la mano hasta que yo termine la traducción de la pregunta, ¿ok? No se puede levantar la mano, todos los gringuitos, nada, no pueden levantar la mano hasta que yo termine la traducción. Miren como que queda bonito un paisa. Okay, let's try.
I showed several pictures.
No, I'm sorry. I will change the rules. Give me the question in Spanish. And in English, I will do it.
No puede responder.
Sí, te perdono. Bueno, muy bien, la pregunta está difícil. La pregunta es, en la imagen que vimos en ondas de radio de este objeto, could you show us the image? Ok. La pregunta es, ojo, alza la mano. ¿Por qué se sabe que en la parte exterior de esta nube está congelado el monóxido de carbono? In English.
Okay, I heard that it was because the carbon monoxide was highly reactive with the other molecule, the N2H+. So if there is a big amount of N2H+ in the outer part of this cloud, it's because it hasn't reacted with the carbon monoxide, so the carbon monoxide must be in the form of ice.
That's excellent reasoning.
Con firmeza, que no tengo camiseta. Okay, Alan, we have enjoyed a lot your talk. Esperamos que ustedes también hayan disfrutado la charla. Y bueno, me imagino que de aquí no, you will not come out from here until 9 o'clock, while all people is taking pictures and asking more questions in English and in Spanish. Pero thank you very much for being here. And we expect that in maybe 2019 you will be here to tell us about what JWST is teaching us about the chemistry in interstellar space. Entonces, queda invitado para el 2019, para cuando lleguen los primeros datos del JWST, para que nos cuente qué se está descubriendo. Carmen también. Ok, los esperamos entonces el próximo viernes en otro coloquio. Muchas gracias por venir.
Chao.
aquí unos volantes de la Universidad de Leiden, del programa de maestría en astronomía de la Universidad de Leiden. Por si alguien pronto está interesado en el programa, es bienvenido por aquí. Why is this in astronomical units and not in other units? Other different units? One light year is about, I don't know, 800,000. So
Jolly.
smaller. Are they too close? This is, can we say,